Um, Last time we introduced a model of a random walk on a graph. We also introduced the concept of total variation distance, and we posed the question of how quickly the distribution of the random walk converges to its invariant distribution in total variation distance. This time we are going to try and answer the question we posed last time. So let me share screen. Okay, so we are going to look at how quickly the distribution of a random walk on a graph converges to its invariant distribution. Let me remind you of some notation. We also use the term steady state or stationary distribution for the invariant distribution, and so we are looking at convergence to the stationary distribution and speed of convergence. Throughout today's lecture, G is going to denote an arbitrary connected undirected graph with finite vertex set V and edge set E. An xt is going to denote a Markov process whose state space is the vertex set. And this Markov process is going to be the continuous time random walk on V, whose infinitesimal generator is minus the Laplacian of the graph. And we are going to denote by boldface P of t the probability distribution of xt. So the random position of the random walk at time t, the distribution of that position. Okay, and we want to ask the question, how quickly does this probability distribution of the location of the random walk at time t converge to this to its invariant distribution pi? We want to quantify this. We want to ask how quickly does the total variation distance between the distribution and time t and the invariant distribution tend to 0. And the way we are going to study this, we are going to first study it for the Euclidean distance, which turns out to be easier using the tools at our disposal. And we'll show, we'll derive bounds on how quickly this tends to 0. And we'll use these in order to get bounds on the total variation distance. And let me also remind you what the Euclidean distance between two vectors x and y is. It's easier to write down an expression for the squared Euclidean distance. So this is the sum over all coordinates of v of xv minus yv squared. And we can also write this as the inner product of the vector x minus y with itself. Again, to remind you of conventions, vectors are column vectors unless otherwise specified, but probability distributions are row vectors by convention. Okay. Okay, so we want to ask the question of how quickly does pt minus pi converge the Euclidean norm of this vector, how quickly does it converge to 0? And let's start by writing down pt explicitly. It's related to the initial condition, the starting distribution at time 0 as follows. It's p0 times e to the qt. So e to the qt is the transition probability matrix over a time interval of size t. And we started with q, the generator of this Markov chain, being minus the Laplacian. So pt is p0 times e to the minus lt. Okay, what about pi e to the qt? Since pi is invariant, if you start in distribution pi, you stay in distribution pi forever, and in particular t time steps later. And so this is the same as pi. Or if you prefer to think of it more formally, expand e to the qt in a power series. Pi is invariant, so it solves the global balance equations. Pi times q is 0. And in the Taylor expansion of e to the qt, you have the identity. Pi times the identity gives pi. And then you have I plus various sums of powers of q. And for each power of q, pi times q to the k is 0. So all we are left with is pi. Okay, so we can write pt minus pi squared Euclidean norm as the dot product of the vector pt minus pi with itself. So it's this row vector times the column vector obtained by transposing it. That gives us a scalar. And pt was p naught e to the minus lt. Pi was pi e to the minus lt. So we've written pt minus pi as p naught minus pi e to the minus lt. And the transpose of that is the transpose of the terms in the product in reverse order. AB transpose is B transpose A transpose. Okay, so we've just written that here. Now L is a symmetric matrix. We already saw that the Laplacian of an undirected graph is symmetric. And you can easily check by induction that therefore powers of L are also symmetric. So L to the k is the same as its transpose. Now e to the minus lt is given by its Taylor series expansion. It's the sum of various powers of lt to the k over k factorial. And by transposing this, because L to the k is its transpose, you get exactly the same thing, which is e to the minus lt. Okay, I have not written out all the steps, but keep in mind that t is a scalar, so in calculating lt to the k, we can write this as L to the k times t to the k and move t around. Scalar multiplication commutes with matrix multiplication. Okay. Okay, so the next thing, so going back to the expression for pt minus pi norm squared, we have here e to the minus lt times e to the minus lt transpose. So we saw this is the same as e to the minus lt. So we want to compute the product of these two matrices. And I claim that this is the same as e to the minus 2lt. And okay, your first remark or your first response might be that this is totally obvious, but I want to warn you that it's not quite as obvious as it seems. And for matrices, e to the a plus b is not the same as e to the a times e to the b in general. So if you expand both sides, take the Taylor expansion of both sides, you can check that in general they are not the same, and I'll leave you to do that. It's a useful exercise to do it. Okay, but there are conditions under which these two things are the same, and they are the same if the matrices A and B commute. So if A times B is the same as B times A. And obviously, if any matrix commutes with itself, so here A and B are both the same matrix, L times T. And so this claim is true. Okay, so what we've shown is the squared norm of pt minus pi is p naught minus pi times e to the minus 2lt times p naught minus pi transpose. And we are going to use that fact to obtain bounds on this quantity. Okay, so we have here some row vector times the matrix e to the minus 2lt times the transpose of this row vector. So we have a quadratic form involving the matrix e to the minus 2lt. And we've studied how to get bounds on quadratic forms. We use the Reynolds Theorem, and the bounds are in terms of eigenvalues and eigenvectors of this matrix of which we are computing the quadratic form. And so that for that reason, we are interested in the eigenvalues and eigenvectors of this matrix e to the minus 2lt. Okay, so let's try to compute those, starting from the corresponding eigenvalues and eigenvectors of L. So say V is an eigenvector of L and that it has the eigenvalue lambda. Then what do we get if we multiply the matrix e to the minus 2lt by the column vector V? First, we can expand this matrix and its Taylor expansion. We get the matrix, the sum over k of minus 2t to the k over k factorial, some scalar times L to the k. So we have the sum of all these matrices multiplying V. And okay, I can switch the order of those, so I can multiply each of those matrices by V and add them all up. That needs a bit of justification, which I'm skipping, but it's true. Okay, so we multiply each of these matrices, the k term in the sum by V, and add up the terms over k. Now, what do we get? L times V is lambda times V. That's the definition of V being an eigenvector of L with eigenvalue lambda. So L to the k times V is just lambda to the k times V by repeated multiplication. And so this is the sum we end up with. So we get a sum of scalars times V, and if you add up all these, this is just the Taylor expansion of e to the minus 2 lambda t, where lambda is now a scalar. So this is a scalar exponential here, while this is a matrix exponential up here. Okay, so we get then some scalar multiple of V, and that says that V is an eigenvector of this matrix e to the minus 2lt with eigenvalue e to the minus 2 lambda t. So that's what I've written here. So what we've shown is that the eigenvectors of the matrix e to the minus 2lt are exactly the same as the eigenvectors of L, and their eigenvalues are related in this way. Now, what do we know about the eigenvalues of L? We already saw that its eigenvalues are real, non-negative. There's the smallest eigenvalue of 0. And since the graph is connected, the second smallest eigenvalue is strictly positive, and all others are strictly positive. Okay, so by this calculation, e to the minus 2lt has eigenvalues which are given by e to the minus 2t times these lambda I. So e to the minus 0 is 1. And because of the minus sign here, the order of the eigenvalues gets switched. So 1 is now the biggest eigenvalue of the matrix. The second biggest is e to the minus 2 lambda 2t, and that in turn is at least as big as these remaining others. Okay, and we also know that one vector is an eigenvector of L corresponding to the eigenvalue 0. So it's also an eigenvector of e to the minus 2lt with eigenvalue e to the minus 0, which is 1. Okay, so we know that much about the eigenvalues and eigenvectors of e to the minus 2lt. So let's go back to what we showed about the squared Euclidean distance between pt and pi. We showed that we can write it this way. And now we use the Reynolds theorem, and let me remind you of that. It says that this quadratic form The maximum of this quadratic form over all vectors x, which are orthogonal to this eigenvector corresponding to the largest eigenvalue. So the all one vector corresponds to the smallest, is the eigenvector for the smallest eigenvalue of L and the largest eigenvalue of e to the minus 2lt. So if you look at vectors in its orthogonal complement, then this Rayleigh quotient is the maximum value of this Rayleigh quotient is the second biggest eigenvalue of e to the minus 2lt, and that is e to the minus 2 lambda 2t. Okay, so that's what the Reynolds theorem tells us. And so we are going to apply this. Okay, we'll come to that in just a second. Now, for any probability vector P, this is a row vector, remember, if we multiply it by the all one column vector, then we are adding up all the elements of the vector P. And for a probability vector, that's necessarily 1. So if we look at this difference P naught minus pi of two probability vectors and multiply it by the all one vector, we get 1 minus 1, which is 0. And that says that this vector P naught minus pi is orthogonal to the all one vector. Okay, and so we are looking at a quadratic form involving this vector P naught minus pi, which is orthogonal to the all one vector. And so the Reynolds theorem tells us that the numerator is bounded above by the denominator times e to the minus 2 lambda t. The numerator the biggest possible value it can achieve is the denominator times e to the minus 2 lambda t. Okay, so in general, for any other vector x orthogonal to the all one vector, this quadratic form is bounded above by e to the minus 2 lambda 2t times the inner product x transpose x, where x is P naught minus pi. Okay, so what we have shown is that the squared Euclidean distance between pt and pi is bounded above by this e to the minus 2 lambda 2t times the square times the inner product of P naught minus pi with itself. Okay, so can we bound this next? So let me remind you, and this should be a boldface pi here, that's a typo. Let me remind you that the invariant distribution for the random walk is the all one vector normalized. It's the uniform distribution on V. And so if we expand out this product, we get P naught transpose minus 2 P naught times pi, and pi is the all one vector upon n. And then we get pi times pi transpose, which becomes this thing. And if you simplify, you have the first term as it is. P naught times the all one vector is 1, so you get minus 2 over n, and 1 transpose 1 is n over n squared is 1 over n. So this is what you get after simplification. Okay, and now for the first term, how big can the inner product of P naught with itself be? P naught is a probability vector, so it consists of non-negative elements which add up to 1. And when you take this inner product, you are taking the square of each element and adding them up. And the biggest that sum of squares can be is 1. It's not hard to see that. And that's achieved by making just a single one of these entries 1, whose square is 1, and everything else gives 0. If you spread out the 1, you get something strictly smaller. Okay, so the biggest this can be is 1, and that's attained if P naught is a unit vector. If you have a deterministic initial condition starting at one single state. Okay, and so substituting this in here, P naught minus pi inner product with itself is bounded above by 1 minus 1 over n, which is strictly smaller than 1. And plugging that back here, the squared Euclidean distance between pt and pi is bounded above by e to the minus 2 lambda 2t. In the lecture notes, I give a slightly weaker bound. I have 2 times this, I believe, and that comes from a slightly weaker bound from here. I didn't use the fact that pi was this thing. I just said that for any 2 probability distributions, P naught and pi, the inner product of this difference with itself can be at most 1, and that's attained if you take P naught to be a unit vector concentrated at some x and pi to be a unit vector concentrated at some other y, and then this inner product can be as big as 2, and that's the largest it can be. But if we use the fact that pi is exactly this, we can get a better bound of 1 rather than 2 on this inner product. Okay, so either way, so either of those bounds is good enough. So we get this bound on the Euclidean distance. And the main thing I want you to notice is that this says that the Euclidean distance between the distribution of the random walk at time t and its invariant distribution decays exponentially. So it goes to 0 like e to some negative power times, negative power of t. Sorry, negative number times t. Okay, and the rate at which it decays to 0 is given by the second eigenvalue lambda 2. Okay, so this tells us how quickly the Euclidean distance decays to 0. But recall that we were more interested in the total variation distance. So we want to now see how quickly the total variation distance decreases to 0. And in order to do that, we want to relate the total variation distance to the Euclidean distance. So that's what we are going to do next. So let's start with any vector x in Rn and then look at the L1 norm of x. So this is the sum of the absolute values of the elements of x. And that is the same as taking the inner product of the vector x and its sign. So the sign of the ith element of the sign of x is the sign of the ith element of x. So that's +1 if that element is positive, -1 if it's negative. And we are going to take it to be 0 if it's 0. Okay. And okay, so just take a moment to convince yourselves that this is true, that multiplying an element by its sign gives the absolute value of the element. And so this is the sum of the absolute values of xi. Okay, so that's the L1 norm. We've expressed it as an inner product between 2 vectors, but then we can bound the inner product using a well-known inequality from first-year linear algebra, and that's the Cauchy-Schwarz inequality. That says that the inner product of any 2 vectors is bounded in absolute value by the product of their norms. So the L1 norm of x, which is this inner product, is bounded by the norms of the 2 vectors whose inner product we are taking. So, and by norm, I mean the Euclidean norm now. Okay, so what's the Euclidean norm of the sign of x, or the squared Euclidean norm? That's just the sum of the squares of the elements. The elements are +1, 0, or -1, so the square is either 1 or 0, and there are n terms in the sum, so this can be at most n. And it's exactly n if there are no zeros in the vector. Okay, so what have we shown? We've shown that for probability vectors P and Q, the total variation distance between them, which is half the L1 norm, is bounded by, okay, this half should be outside the square root. So it's the sine of the L2 norm of the sine of x gives us a square root of n. So it's square root n over 2 times the L2 norm of P minus Q, the Euclidean norm of P minus Q. So the total variation distance is bounded by a multiple of the Euclidean norm, and the multiple depends on the dimension. It grows like square root of the dimension. Okay, so what have we shown so far? We've shown that the Euclidean norm, the Euclidean distance between pt and pi decreases to 0 like e to the minus lambda 2t. And so if the cardinality of the vertex set is n, then the total variation distance decreases by the typo carries through. So square root n over 2 times the Euclidean norm, hence square root n over 2 times e to the minus lambda 2t. Okay, so that's how quickly. Okay, so essentially the same thing. The total variation distance also decays to 0 exponentially in t, but it can be large for some time up to some multiple of log n, and after that the decay kicks in. Okay, so suppose we are given some epsilon strictly positive and we want to know how long we have to wait till this distance gets smaller than epsilon. Then what we can show is that irrespective of the initial condition, this distance will decrease to something smaller than epsilon if square root n over 2 times e to the minus lambda 2t is smaller than epsilon, and same typo again throughout the rest, in fact. Okay, so it tells us how big we have to pick t in order to make this smaller than epsilon. And okay, so with some simplification, we can write that this total variation distance is smaller than epsilon if t is bigger than this whole thing. Okay, again, the typo will have some effect here. But the main things to keep in mind are you have t should be at least as big as 1 over lambda 2 times something that grows logarithmically in n, the size of the state space, and it grows logarithmically in 1 over epsilon. This says how close you want to be. So the closer you want to get to the invariant distribution, the longer it takes, though not by much, only logarithmically in how close you want to get. And also the bigger the state space, the longer it takes. But again, here there's only logarithmic dependence on n. And so the main term really is this lambda 2. Lambda 2 determines how quickly this convergence happens. Okay, a bit more terminology. So we are going to define the mixing time of a Markov process. So this can be defined for Markov processes in general, though we are mainly interested in it in the context of the random walk. But let me introduce the terminology in general. So we have some continuous time Markov process xt. And let's say it has a unique invariant distribution pi. Then if we fix an epsilon positive, we define the epsilon mixing time of the Markov process, which we denote this way, as the smallest time for which the total variation distance between the distribution of the Markov process at time t and the invariant distribution is smaller than epsilon. And this is true no matter what initial condition you start in. So for arbitrary initial conditions, it should be true that this that you are not further than epsilon away from the invariant distribution by time t. And taking the maximum over initial conditions ensures that. Okay, so intuitively, T mix epsilon is the first time for which no matter where you start, you are guaranteed to be within distance epsilon of the invariant distribution. Okay, and the term often we ignore the epsilon, we take a specific value, which by convention is 1 over e. Some other authors use 1/2 as the convention. It doesn't matter too much. So long as it's strictly smaller than 1. So for this constant value of epsilon, the time to get within that distance epsilon is called the mixing time. Okay, and what we have shown is that if our Markov process is a random walk on a connected undirected graph, its mixing time grows like the reciprocal of the second smallest eigenvalue of the Laplacian. That's the most interesting and important term in this expression. And then in addition, it grows with the size of the problem, but slowly it grows with how close you want to get, but again, slowly. And this is the main result of this part of the talk. Okay, so this is the main thing regarding random walks. I just want to make a couple of remarks. So we focused on analyzing the mixing time for random walks on a graph, but all the definitions carry through for general Markov processes. And it's in that context that this problem is very interesting and important. So there's a whole class of techniques for sampling from a given distribution. If you say you're given a probability distribution pi on some large and complicated state space, and you want to get independent random samples from this distribution, there's a technique for doing this called Markov chain Monte Carlo. You try to come up with a Markov chain whose invariant distribution is the distribution of interest, and it's often not hard to do that. And then you simulate this Markov chain. And if you simulate it for long enough, then you should be close to the invariant distribution, which is the one you want to sample from. So if you simulate your Markov chain for a long time and then take a sample from it, you get a sample from the desired distribution. The question is, how long is long enough? And this is often very hard to tell. If you can get some bounds on how long is long enough, then that's very useful for applying this technique of Markov chain Monte Carlo. So deriving bounds on this time is a very interesting problem. And okay, we've done that for one example of a very easy Markov chain. In general, this is quite a hard problem. But I should mention that much of the analysis we carried out here goes through with minor changes for reversible MCMC, for reversible Markov chain Monte Carlo. Okay. And that has to do with the fact that we used the symmetry of the Laplacian matrix heavily. And okay, you don't need symmetry, but you need something close to symmetry. And that reversibility is one of those things which is close enough to symmetry. So the analysis carries through with minor changes for reversible Markov chains, but it doesn't carry through for non-reversible chains. And in the context of Markov chain Monte Carlo, this kind of analysis is very important. So it's It's just something that that might be useful for you to know, and links the topic of this course to some other important topics in probability and statistics. Okay, so that's the end of this lecture. And next time we are going to look at this lambda 2, the second smallest eigenvalue, and say, can we give some bounds on this eigenvalue in terms of some properties of the graph G? Okay, I'll leave that for next time. I'm going to stop sharing and stop recording.